Okay, good morning, everyone. Let's get started. Okay, so where are we in terms of learning databases, right? So essentially, over the last couple of weeks, we learned about how to essentially query a database system as a user. So essentially, there are two interaction models, right? So you can ask the database to create a table, right? Whenever you do that, database system going to actually store your information on the hard drive, right? So, and then you can actually start to put data into your relation. You can insert all those information tuple by tuple, or you can have maybe a very large CSV file that you just put them all together into your table. Once your data is actually in the database system stored on hard drive, you can actually query it, right? So we talk about how to do it by writing a SQL query. And if you write a SQL query, what's going to happen under the cover is the database is going to bring that information from the hard drive to the DRAM and bring that from DRAM to you as a user. And the goal of the database is try to make this process as declarative as possible. Right? We keep talking about this word, declarative. You as a user tells the database essentially what you want instead of how to get it from the hard drive. And the job of database is really try to optimize the execution or bring that piece of data from the hard drive to you as a user. And starting from last lecture, we kind of switch gear a little bit. Instead of talking about how to query a database system as a user, we talk about how to essentially build a real world applications, right? So now you as a user knows how to interact with the database system. But if you have one application you want to build, you kind of need to think about how to translate that into a sequence of queries to a database system. How can I design my schema? How can I model my application, right? So from last lecture, we start to talk a little bit about how to use the database system to build some kind of real world applications. We talk about the principles. If you think about that process, right, building a real world application in a database system can be naturally like fit into essentially three different stages. So at the very, very beginning, the first step is called conceptual modeling. So in that step, you as a user have a real world application in your mind, and then you try to describe it precisely to try to describe all those concepts, right, in that application. And after you have that, the second stage is called logical modeling, where you try to map all the concepts you have in your conceptual model into a logical representation. And depending on what type of database you are using, that logical representation may be different. If you are using a relational database, for example, that logical representation will be relational model. You kind of model your data as a whole bunch of relations, right, which look like a whole bunch of tables, right? You try to map all your concepts in your application into that bunch of tables. If you are using maybe some semi-structured databases, like those, if you are using MongoDB, right? So then your logical model is something different. It's more of a hierarchical structure. And after you have that, so the third phase of building the application is called physical modeling, right? So that is where you kind of implement this logical representation concretely on some hardware, right? So for each of these stages, there are a lot of tools that database provide to help you, and we are going to go through them one by one. So just to refresh our memory, right, to make sure we are on the same page when we talk about these three different stages, this is just one example we walked through in the last lecture. So assuming you want to build one application here, and here the data I have is essentially, I want to build a toy, right? So I need to store the information about that toy, and I also need to store the information about different parts that I need to assemble to build that toy, right? And for each part, I have a whole bunch of attributes, the name of the part, right, the picture of the part, quantity, so on and so forth. So as a user, right, so when you try to build this application, you as a user can always kind of describe this application in natural language. Right? For example, we can just write a whole bunch of sentences in English and try to describe this application. Of course, this is not machine understandable, right? You type it into a machine, like machine will not understand you, right? But nevertheless, you can describe it, right? So here we want to build one application where we have a whole bunch of products, right? Each product is a toy we want to build. Each product has a name. A product contains a set of parts. A part also has a name. Like a part also have a whole bunch of properties like unit cost, quantity, total cost, so on and so forth. Of course, this is not machine understandable, right? To really build the application, you need to turn that into something machine understandable, right? So, and one way to do that in the conceptual modeling part is by drawing an entity relationship diagram that looks like this. In the last lecture, we talked a little bit about some basic concept in doing this via this kind of diagram. And we also talk about its formal semantic. So once you have that, right? So logical modeling part is really try to map this conceptual model into a relational model if you are using a relational database, right? So in this context, you are going to have a diagram look like this, and then you are going to have a set of relations kind of as an output of this logical modeling process. And then the third phase is physical modeling. It's really the physical implementation of this logical model. You have all those kind of like relations in your logic model. And here we are going to talk about the physical implementation and the representation of those relations on concrete hardware or concrete type of hardware. Okay. So this is the three different phases. So in this lecture, we are going to talk about two things. We are going to continue our discussion about conceptual modeling. There's something we haven't covered yet from last lecture. And then we are going to talk about logical modeling. That is, given an entity relationship diagram, how can we translate that into a relational model? Okay, so let's start from ER diagrams. So just to refresh our memory, right? So let's look at one example. So far, we have been talking about a whole bunch of concepts like entity set, right? Attribute, relationship, key, role, right? So you should be able to read ER diagram like this after Wednesday's lecture, right? For example, here, right? So what we are trying to convey to the machine about our application is that the data I have is organized as follows. I have 4 different types of entities in my application. I have students, I have lecturers, I have assistants, I have professors, right? If you take, for example, professor, there are 4 attributes for each professor. There's a personnel number, there's a name, there's a room, there's a level, so on and so forth. And in my application that I want to build, I also have a whole bunch of relationships between all those different type of entities. For example, if you read here, right, you can see, one relationship that I want to have in this application, or I have to have in the application, is that professor gives lecture, right? So essentially, I want to store a whole bunch of pairs between professor and the lecturer to really convey the information that some professor teaches like some lecture, right? So you have the relationship here. Okay? And then sometimes like one relationship can be between 2 entities of the same type. For example, the requires relationship is between 2 entities, both of the type lecture, right? So one lecture is a prerequisite, one lecture is a follow-up. So to really distinguish between these 2 different participants, right, of the same type, you can have the role of participation, right? One lecture here is a prerequisite, another lecture here is a follow-up, right? You can just write the role here. So I think we can all read this. The beauty of an ER diagram is that it really gives you a kind of intuitive way to intuitive yet precise way to describe your application. So last time we kind of also talked about cardinality, which is something could be a little bit confusing. So let's just refresh our mind on that. So the goal of cardinality is really try to tell you, if you give me a relationship look like this, right? So if you do not tell me cardinality, right? So what is a valid like relation instance here, right? So if you do not give me cardinality, right? So an instance of this relationship will be any kind of finite. It need to be finite because of database. Finite subset of the cross product between all those entity sites, right? So if you do not have this like any cardinality constraint, you give me relationship R look like this, right? So one instance of this relation will be essentially a set of 4 tuples, right? So tuple with 4 values. One value is A and B and C and D. But sometimes I want to describe some constraints, right? I do not allow all the possible subsets. I want to say, okay, maybe there are constraints like, for example, if I know the value of A, B, and D in this relationship, I can decide the value of C that uniquely associated with only one value of C, right? For example, you want to model information like one professor can teaches only one lecture per semester, for example, right? You have all those constraints about what is a valid relation. So if you want to convey information like this, right? So we talk about this 1 and n notation, right? So essentially you can write either 1 here for each edge, or you can write n for each edge, right? So if you have a diagram look like this, so the semantic of it is that you take all those 1, for each 1, you generate 1 constraint. For example, for this one associated with A, essentially you are saying that, okay, in this application, if you give me the value of B, C, and D, I can uniquely identify A. Okay. Similarly, for this one associated with C, what we are trying to say is that if you give me the value of A, B, and D in this application, I can uniquely identify a unique value of C. Okay. So you actually do not specify anything if this n, okay? So precisely, this is what you are trying to describe, right? So for any ER diagram, you can translate that into a sequence of first order logic sentences. And then the constraint you are specifying by drawing a diagram look like this is precisely what we have been talking about. That is, for each of this 1, you introduce 1 first order logic sentence about the constraints on cardinality. So an validated database instance modeled by your conceptual model need to satisfy these 2 sentences. Okay. So intuitively, this means that if I know ABD, I know C. If I know BCD, I know A. Okay. So and we talk about some examples, right? So if you have an ER diagram look like this, so what does this mean? Right? It means that okay. So if I know the value of student and professor as a combination, I should know the value of topic, right? If I know the value of student and topic, I know the value of professor, right? So that actually defines a whole bunch of possible instances that's consistent with this model. For example, right? So if you look at database instance look like this, this is actually not allowed in this model because you have student and student 1, professor 1, student 1, professor 1, right? Both of them have the same value in the combination of student and professor, but they map to different topic, right? And in this case, it's clearly not possible because from the ER diagram, if I know student and professor, so I should be able to like uniquely identify a topic. So this is actually not allowed under this model. And when you go back home, you can actually go through this same exercise, right? So all of this should be pretty natural after last lecture. Okay, and we can try to read this diagram together, right? So essentially, if you look at all those kinetic constraints, right? So if you look at the gates, you have n here, you have 1 here, right? This essentially means that if I know the value of lecture, right? So I should be able to decide the value of professor, right? So which means that 1 lecture can only be taught by 1 professor, right? I cannot have 2 professors teaching the same lecture in this model. And also one professor can teach multiple courses, and there's no constraint in this model, right? So, and you can actually try to read it by yourself, right? So that should be pretty natural. Okay, so this is just one notation that you can express cardinality. And we can actually have another notation that's a little bit more expressive. So that is something we call min-max notation. So in this notation, to express cardinality, we kind of write two numbers associated with each edge. And that is the minimal amount of time and the maximal amount of time the same entity A can participate in this relationship. So for example, if you have a ER diagram look like this, what you are trying to convey is in my database, right? R. So like in my database. So if I look at the relationship R, right? So the same entity A can only participate, should participate at least a minimum amount of time, but it cannot participate more than a max amount of time. So this is essentially what we are trying to say. You can go a little bit more formal. Essentially, if I have a ER diagram look like this, I'm introducing three logical constraints on what a valid database instance should satisfy. So the first constraint is associated with A. Essentially, you are saying that for any entity XA, okay, you need to have there's kind of exist at least a min, at most a max number of XB and XC such that XA, XB, and XC participate in R. Okay, so similar, you have that for XB and you have that for XC. Okay. So this is just another notation for you to express cardinality constraints. So one thing that we can see is this notation is more expressive compared with the 1 and n notation that we just introduced. Meaning that it can actually, like essentially, like for any constraint that you can express in the 1 and n notation, you can express in the min-max notation. For example, if you have a kinetic constraint look like this, right? You have n on the professor side, you have 1 on the course side, right? Which means that if I know professor, I know course, right? It actually means that like in the database, professor can only like one professor can only participate in one of this relationship, right? So like otherwise you are going to violate this constraint. So essentially that's actually equivalent to a ER diagram look like this, which means that a single professor can participate in like either 0 times, meaning that it doesn't participate in any relationship, or it can only participate in one of this relationship. And this just means one professor can only teach one course. Okay. So essentially, like these two are not equivalent. So the min-max notation can actually express actually more type of kinetic constraints. But for any kinetic constraint that you can express in the 1 and n notation, right, you can always express it in the min-max notation. Okay, so let's look at one example. So assuming we want to model some geometric objects, right? So we have, oh, I think we have one question. Go ahead, just speak up.
Yeah, hello. Can you go one slide back? I wanted to ask you something on the relation on the bottom left. And I was wondering, since you said for each professor you can identify a unique course, is it in the bottom left possible for a professor to not teach a course?
Oh yes. So in the bottom left, it is possible for professor not teach a course. That's true. Yeah.
Okay, so if we have a professor, we cannot uniquely identify a course for this particular professor since he doesn't teach a course at all. So that's where my confusion is coming from.
Oh yeah. Okay. So that's a very good question. So okay. So if you have something look like this, a professor doesn't need to participate in a relationship. It means that as long as okay, so it means that for any professor who participate, you need to be able to uniquely identify the course.
Okay. Thank you.
Yeah.
That helped me. Thanks.
So like that's why it's kind of equivalent to this one, right? So the one professor can either essentially participate 0 times or 1 time.
Thank you.
Right. Yeah. Let's see. Yeah. So if you look at this, right? So you go back to the formal semantic. You always go back to the formal semantic. The formal semantics, like for all those entities, so you need to have them participate and then you imply, right? So like if one professor doesn't participate in any of the relationship, this part is false. So this is always true, right? Make sense? So from the formal semantic, so like you can just derive that, okay? So and that's why this is like imply like the relation is here. So if you look at the second notation, second notation, the min-max notation, right? So the left-hand side of the mathematical imply is the entity, not the relation. Okay, so this actually means for any of those entity in this type, you need to have this. Okay, but for the one and n notation, right? So left-hand side of the imply is the participation in a relation. Okay, so if the entity doesn't participate in any relation, that thing is going to be false and going to be fine. So like the imply going to be evaluated to true. Okay, perfect, great. So now let's look at one example. Okay, so let's model some geometric object. For example, we have a polyhedron, right? As one object, it can in a 3-dimensional space, right? So it can have multiple surfaces, right? For example, here you have a cube, right? So you have, I don't know, 6, 8, I don't know, yeah, some number of surfaces, right? So and for each one, I mean that's another object in your database. And then for each surface here, you have 4 edges, right? And then for each edge, you have 2 nodes, right? So how can we model this? Yeah, so you have essentially 4 entity sites. You have polyhedron, you have surface, you have edge, you have node, and then you can connect them with different relationships, right? A polyhedron can have multiple surfaces, right? And the surface can has multiple edge, and edge has multiple node. So the interesting part is about the cardinality constraint, right? So in this example, right, if you look at polyhedron and the surface, right, so what cardinality constraint we should write here? So here, right, so if you give me a surface, right, so I should be able to uniquely identify polyhedron, right? So like so essentially you have 1 here, you have n here, right? So that's why I can look like this. And if you look at the surface and the edge, right? So in this example, right? So if you look at this edge, right? So it can actually be associated with actually 2 surfaces, this surface and this surface, right? So there's the intersection of like of different surfaces, right? So essentially there's actually a many-to-many relationship. One surface actually is associated with multiple edge. So here one surface associated with 4 edges, right? One edge can also be associated with multiple surfaces, right? Because there's intersection. So there's a many-to-many. Similarly, you have edge and node, right? So one edge contains multiple nodes, right, in a 3-dimensional space. And the node can be associated with multiple edges because if you look at this node, right, so it's actually associated with like 3 different edges. So there's many-to-many here. So and you can see by using the min-max notation here, something like this, we can actually make that much more precise than the 1n notation. So for example, if you look at like here, right? So one polyhedron, right, should have at least 4 surfaces in our 3-dimensional space, right? So you can have cardinality look like 4 and star. Star means just like infinity, right? So which means that one polyhedron object should participate at least 4 times in my database. It need to like has at least 4 surfaces, and you can have as a maximum you can have as many as you want. Right? So and then a surface should participate essentially like one and only one time, right? So in this example, and then similarly, right? So you can have like one surface in 3-dimensional space should have at least 3 edges, right? So and yeah, so and for polyhedron, right? So one edge can only participate to, essentially exactly 2 times, right? In the 3-dimensional space, right? So and similarly, right? So this all makes sense, right? So as you can see, right? So if you do this min-max notation, you can express actually kinetic constraint in a more precise way, right? So compare with the 1 and n notation. Okay, so this is about cardinality. Okay, so I know it could be confusing, but one thing to do is when you go back home, right? Look at the examples in the exercise and the textbook, and you try to kind of go through the process of reading about cardinality, right? So and after practicing 1 or 2 questions, this should be really, really clear. Whenever you are not sure about what cardinality means, always go back to the formal semantic. Okay, so we provide the formal semantics, right? So I mean, the reason behind it is if you do not have that formal semantic, sometimes this could be confusing, right? For example, you have many-to-one relationship between professor and the course, that professor must kind of participate, right? So in any relationship, right? If you go back to the formal semantic, you will always have that. Okay, cool. Yeah, so I think there's one more question. Go ahead.
Okay, I'm a bit confused because the 1n notation and the min-max notation seem to not match up for me, because, for example, for polyhedron and surface, I would read it that one polyhedron has many surfaces, and then I look at the n below. But on the other hand, when using the min-max notation, I say a polyhedron, and then I look at the upper pair. So this is what confuses me, because first for 1n notation, we looked at the n which is below, and now we look at the pair which is above. You know you understand my confusion?
I understand your confusion, right? So if you look at the 1n notation, the many part is here. Is the n is the many part, right? So I have one polyhedron, right? So I have multiple surfaces. Yeah, and if you look at the min-max notation, the many part is the opposite, right? So one polyhedron can has many surfaces, right?
So it is in fact like exchanged the way you read it. Stephen.
Yeah, exactly, right? So the many parts start to change, right? So because simple, like why? Because if one polyhedron is associated with many surfaces, in the database, one polyhedron object will have multiple participants, like we'll have multiple participations, like in relationship, right? And because here I'm writing the participation number here, right? So essentially, like this one will be larger than 1. So because in the min-max, I'm writing the participation, and in the 1n, I'm writing 1 and many, right? So that's why it's opposite. Yeah.
Okay.
That makes sense.
Yeah, thanks you. Thanks for the clarification.
Yeah, cool. Yeah, so I know a little bit confusing, but always go back to the formal semantic, and after practicing multiple questions, it will be clear. Okay, yeah. Okay, great. So that's all about cardinality. So now let's look at another concept in entity relationship diagram, and that's called weak entity. So in many applications, you will see scenarios look like the following. That is, the existence of some entity relies on other entities, right? So here's one example. So let's say we have 2 buildings, CB and the main building, okay? So that is one entity type. We have building entity. And then we have the room entity. So CAB has multiple rooms, and the main building have multiple rooms. And each room has an ID, right? For example, both building has a room F1, right? So now the question is, a room cannot exist without a building, right? If you don't have a building, I don't have room, right? So there's those kind of hierarchical structure here. So the question is, because both of these two rooms, like one in CAB, one in the main building, have the room number F1. What is the key for the room object, also for the room entity? So clearly, I cannot use the room number as the key because I could have two rooms with the same room number, right? So the key of a room has to be the combination of the building ID, right, and the room number, right? So that's the thing that can uniquely identify a room. However, if you just use that combination, you're actually storing additional information, right? Because when I store the building information, I already have that, right? Then how can we model it? So in this case, we can actually introduce a notion called a weak entity, meaning that some entity relies on another entity. For example, here, room is a weak entity relies on building. You cannot have a room without a building. So in this case, we can write it as this in the ER diagram, right? So we have the double line, like a diamond, right? So we have double line rectangle, right? So to say if you have something like this, then I have the room as a weak entity of building. And here, the key of the building is a building number, which is fine. And then the key of the weak entity, and you only write room number here, and you just have the dotted line underneath the cover. So like that, not underneath the cover, but the underline is using the dotted line, right? So when you have this, you are actually saying that, okay, room cannot exist without building. It's a weak entity. Whenever I try to identify a room, it's always a combination of the weak key, the room number, and the key of the strong entity, which is the building number. So that is what we are trying to convey to the system. That is, whenever I try to identify a room, it's always a combination of two values, the building number, the key of the strong entity, and the key of the weak entity. Okay, so combination of it going to identify a room. So that's what we are trying to do here. Okay, so here the key of the room is going to be building number and room number. So one thing that is interesting is what is the cardinality of the located in relationship. So here essentially it's always many to one from room to building, because one building can have multiple rooms, but one room need to kind of like appear in only essentially one building, right? So essentially, yeah. So the cardinality of this is actually many to one. Okay. So and this also when you have a weak entity, right? So this also implies that there cannot be a room without a building. Okay. Okay. So another concept in ER diagram is generalization. Okay. So here the information that we want to represent it as follows. We have one entity side with a professor. We have another entity side, students, right? Both of those entities are people, right? So essentially they share some common attributes, right? So how can we represent that, right? We do not want to write the same attribute shared by professor and student multiple times, right? So we want to model this type of hierarchical structure between different entity sites. So here, once you can do is to have this kind of is-a relation, look like this. So here, if you have something like this, it actually means that, okay, I have essentially three entity sites. I have professor, I have students, I have person. And professor is a person, student is a person. It means that for any entity, in this entity set professor, right? So I need to share all the attributes that you have as a person. Okay, if a person have ID, has nationality and passport, right? Then any professor here will also have that 3 attributes. And similarly, any students will also have that 3 attributes, right? You can have additional attribute for professor, have additional attribute for students, but when you have this type of generalization structure, it means that for all the attributes specified for person, professor will also have it. Okay, and also here it also means that both professor and students will also share ID, and which is the primary key. Okay. So this is about generalization. Really pretty natural. Okay. So another thing about ER diagram is that there are actually a lot of flavors of an ER diagram. So in practice, you will see a whole bunch of different ways to draw the same thing. Okay. So for example, this is actually three different ways to specify the many-to-one relationship, right? In some ER diagram, you are going to look at kind of this example, right? You have n, you have 1, right? And for some ER diagram, right, you are going to see, okay, so they actually use this kind of directional arrow up here, right? So there's a like one line pointing from E2 to E1. It means that there's a many-to-one relationship, right? And sometimes people use this type of notation, right? So you have this like 3 different lines, right? So as a many part, right? And you have this one as a one part. If you look at this, it's actually there's a many-to-one relationship from course to instructor, right? So sometimes you see different flavors in practice, and there's no way we can enumerate all of them. One thing to make sure is that you do not get surprised when you see a different flavor in practice, okay? So when you are building real world applications or when you are reading other people's ER diagram, right? Do not be surprised when you see something that you never saw before, right? Because there are different flavors here, right? So in the exam, we will always use one flavor, which is we introduced in the course. But when you really go to the real world and try to build something real and interacting with other people using different systems, right? So you will see they are going to be different flavors. Just don't be surprised, okay? Whenever you see something you don't understand, just look it up, right? So it will always be somewhere, but yeah, don't be surprised when you see something different, okay? So yeah, so let's look at 2 concrete examples, right? Maybe let's go through one of them, and for the second one, you can do the exercise when you get back home. So here's one example. I just actually Google like ER diagram like on Google, right? So and then this is one of the top result it returned. So let's look at this. I actually don't know what this trying to model, right? But we can actually try to read this together. So essentially, if you look at a ER diagram look like this that someone gave you, what application do they have, right? Essentially, in this application, they have essentially 6 different type of entities. There's employee, right? And then there's a generalization here, means that there are actually 2 type of employee, mechanic and salesman, right? And then there's another 2 type of entities, car and client, right? And then there's some weak entity called repair job, right? Which means that you can actually have multiple of these entities, weak entities, kind of associated with a car, right? It seems that you can actually repair a car, right? So, well, of course, a weak entity because I cannot have a repair job without a car, right? So the existence of repair job depends on the existence of car, right? So if you look at this repair job, right? So the weak key is number. It seems that you have one number for each repair job, right? And then because of weak entity, right? So it's also, if you want to kind of identify a repair job, you need to have the combination of number and the license of the car, which also makes sense, right? So, and then there's a different relationship between them, right? So there's a DAS relationship between a mechanic and repair job, which means that a mechanic actually here, because there's no cardinality, it means that multiple mechanic can actually conduct the same repair job, right? And vice versa. And for employee, you have the key, which is number, right? So, and for both mechanic and salesman, they will actually share all those attributes. Salesman will also have a name, has a number, and primary key is going to be number, right? Because of this ESO relationship, right? And similarly, you have a relationship saying that, for example, salesman can buy a car, right? So, oh, sorry. Oh, no. So like you have client, right? You have salesman, you have car. If you look at base, right? So it's a three-way relationship between salesman, car, and client, right? I think this actually pretty much means that like client going to buy a car, right? Via the salesman, right? So, and similarly, you can have the three-way relationship between salesman, car, and client, which is sale, right? And this relationship also have attributes, right? So this actual attribute on which day you sell the car, so on and so forth. So I think we have pretty much all the knowledge that we need to read this ER diagram, right? So, and you can see this is a conceptual model, meaning that if I gave this ER diagram to any person, right, he or she will actually read this diagram and understand what type of data is actually allowed in this application, right? So I think there are multiple messages in the chat window. We have one question. Does that mean buys and sells are not tables because they have attributes? No. So buys and sells are always relationships, right? So here, like pretty much here, I mean, essentially they have attributes, meaning that for any single participant, like essentially, if you think about relationships, right? For sales, and that's always a tuple with three values. You have salesman, you have car, and you have client. When you have attributes, it pretty much means that for any single tuple with three values, you also associate with a date and the value and the commission. Okay, so like later on we are going to talk about how to represent kind of relationship using tables, right? But here whenever we have an ER diagram, and this pretty much means this only means relationship, right? So you can implement that using like later, like using tables, using some other structures, right? But that's the logical modeling part, right? So here essentially means that I have a relationship here. Whenever you have a relationship, you have three participants, a salesman, a car, and a client. For any single of those combination of values, you have an attribute, date, value, and commission. Okay, so this is just another example, right? So this just the thing I get from Wiki, right? So, and you can just read it and you can roughly understand what it's doing, right? And you can also precisely understand what type of data is actually allowed, like in this application. Okay, and that's the goal of conceptual modeling. Give people a very precise way about what application you are trying to model, what data you are allowed. Okay, great. So whenever you are doing this ER diagram, because we are modeling a real world applications, it's very hard just to say some ER diagram is good, some ER diagram is bad, right? But for one application, there's always multiple ways that you can model it. So the best thing we can do is to give you a whole bunch of principles about what is a good model, right? So first thing is that a good model should reflect reality, okay? So having a model doesn't change the reality, right? So you need to have a model that's actually hopefully consistent with reality as much as possible, right? So I mean, you can draw a ER diagram saying that person belongs to the type of entity that can fly, right? But that doesn't mean human can fly in real world, right? So your model doesn't change the reality, right? So no matter how natural your model is. So, and a good model should actually reflect the application that you want to build, right? So that's a very important principle. And second, whenever you are modeling stuff, ideally we want to avoid redundancy, right? For example, here, right? So you could have model look like this. I have assistant and a professor. Assistant works with the professor, right? So, but I could say, okay, so one assistant also have advisor, but assuming in your application, this advisor and the professor the assistant works with is always the same person, maybe you do not want to have that, because if you do this, you are going to have a different, like redundant information, right? So you want to avoid that. And also you want to keep the ER diagram as simple as possible, right? You want to have an ER diagram that model enough amount of information that you need to build the application, but not more than that, right? So for example, you can have a very convoluted way to model assistant works with a professor like this, assistant works with an advisor, advisor is a professor, right? So, but if this type of relationship is not useful in your application, you might want to simplify that, right? So you want to make the ER diagram as simple as possible, right? But not too simple, right? You still want all the information to be there, but you want to simplify that as much as possible. Okay, so let's take a break, right? So after 15 minutes, let's get back and continue, okay? If you have any questions, I'm here to answer them. Yeah, just speak up, yeah. Okay, so we have one question. I think that's interesting. Yeah, so I haven't go through all the message in the chat window yet, but we have one question that is, in the employee, engineer, and salesman example, how can we know which is the parent, right? So that's a very good question. So like in our notation, okay. So you have the essentially arrow here, right? So we have professor essentially 0.2 person. Okay, so that actually means person is a parent. Okay, so essentially you have the so if you look at this professor and student 0.2 this relation, and this relation 0.2 professor. Sorry. I mean this relation 0.2 person, right? So I mean this is just one way for us to like to do it. Okay, make sense? Yeah, and if you go to this flavor, I'm actually not sure. Yeah, for this flavor, I don't know, right? So I mean, you can see this is actually a triangle here, right? So I mean, there must be some way for you to do it. Yeah. Yeah, but in exam we will always do our flavor. Okay. Yeah. So which should be clear.
Professor. Professor, are you here?
Yeah, sorry. Sorry. Go ahead. Yeah,
if you
spend some water. Yeah, go ahead. Sorry.
If you go again to the mechanic and salesman example.
Yes, this one.
Here for sales, we have the attribute value that's only dashed, and for client, we have the attribute phone that's circled twice. What does that mean?
Oh yeah. So that's something that we didn't introduce. I actually don't know. Yeah. So there are actually more things in the ER diagram that we haven't talked about yet, right? I think in the textbook you will see it. Yeah. Sorry for the example. I actually don't know. Yeah. Sorry.
Okay.
Yeah. So like we can try to Google it and you will actually see it. Yeah. So like attribute double line. So I'm pretty sure you will get that. Yeah.
Okay, I will do that. Thank you.
Yeah. Yeah, so just to answer your question about what is this kind of like a dotted line and the double line here, right? So I literally just Googled essentially like attributes double line ER diagram, right? So essentially you can see, so essentially those like dotted line is kind of what they call derived attribute, which means that the value of this attribute can be calculated using essentially other attributes, right? For example, here it means that I don't know this example, but essentially like this thing can be calculated using other attributes. And then for this kind of double line, right? So it's multi-valued attribute, meaning that essentially that attribute can take multiple values, right? Instead of only one, right? So and then you can see there's a whole bunch of other things, right? So like the full specification of ER diagram is actually pretty complex, right? So and yeah, whenever you are reading a real ER diagram, just whenever you see something that you don't know, just look it up, right? So there's no way we can cover the whole thing, right? So like in the lecture, yeah.
Okay, thanks a lot. You were faster Googling than I was.
Yeah. So and also read the book, right? So like so I think the book has actually more things than we talk about. Yeah.
Okay. Thanks.
Okay. Sorry. Okay, so let's continue. Yeah, so there are multiple design principles here, right? So, and just as a rule of thumb, right? So there are sometimes when you model stuff, you sometimes you could kind of get confused about whether you should model something as attribute or you should model something as an entity, okay? For many cases, this is very clear, right? So for some cases, for example, your value is a really concrete value, right? So, I mean, of course, it's going to be attributes, right? So sometimes it doesn't make sense to model something as entity. It doesn't make sense to make something attribute. But somehow there is kind of the gray area that you could go either way, right? You could model something as an attribute, you could model something as an entity and connect that like with the other entity using some relationships, right? So, and of course, it's always application dependent, but as a rule of thumb, right? So you model something whenever you are confused in your application, often the time that you model something as an entity, if that concept has more than one relationship, right? So, and you model as an attribute, if that concept actually only has one-to-one relationship with an entity, yeah, so, and it makes sense. Yeah, so like otherwise, it's very hard to do that as an attribute, right? So, and also in real kind of applications, like we talk about the ER models that looks very simple, right, in this lecture. But in applications, ER model can be really large, right? So there are like most of the realistic models are actually, if you print it out, it's going to be on the single page, right? So, and sometimes the best practice is for you to partition entity relationship models. For example, if you want to model the whole ETH, right? So you could have one ER model for the library, one ER model for research, one ER model for finance, right? And then you cannot put them together, right? So otherwise it gets messy really fast. So, and there's some rule of thumb for good models and bad models, right? So, but whenever you are modeling stuff, right? So you think at the logical level, right? We model it. You do not model like redundancy. You do not model optimizations, right? For example, in some database, maybe it makes sense to duplicate some information because that makes the query really fast, right? So for example, if you know, in my query, I always kind of like whenever I'm querying students, I always get, for example, the lecture the student is taking, right? So that's like when you are doing a database, maybe you kind of drawing that two tables together, you always store the information together, right? But when you model it, they are always separate, right? So you do not model the tricks that you are doing to improve the performance, because now we are actually trying to model the concept instead of kind of the implementation, okay? So, and also you want to make sure your model is as simple as possible, right? So like a very simple proxy is you count how many entities you have, right? So you try to, you try to decrease that. And also you want to make your model as concise as possible, as correct as possible, complete, comprehensive, right? So that's a whole bunch of rule of thumb. When you are building the real thing, you will realize it's actually more complex than it might sound like, right? So, and the best way to do it is to practice. Okay, in this course, we are going to give you the principle, but when you go to the real world, just keep them in mind. But this is something you need to practice at least once, right, to get a feeling of, right? So, and a good proxy is go to the actual session, right, and try to understand those examples. They are still simple, right, but that will help you to get some feeling about how to model stuff. Okay, so I see someone raise hand. Just speak up. Yeah, if you have any questions? Yeah, go ahead.
I mean, I wrote the question in the chat. I was just wondering what you meant with most realistic models are larger than a page. what you mean exactly with a page? Like
oh yeah, sorry. I mean a physical page. Yeah, so like one piece of paper. It's an A4 paper, whatever. Yeah. Sorry, it's not precise. Yeah. So I simply means it's large. Yeah. Sorry.
Thank you.
Yeah. Okay, great. So now let's look at one example, right? So, and there are a lot of tools that we can use to model your applications. And many of them will actually kind of support, like if you have a diagram, right? So you are going to semi-automatically translate that into a relational schema. So we'll just see one example. I mean, it's not the best tool in the world, right? But it's simply, I mean, like it's simple enough and free. So let's try to model something together, right? So we will not model the whole thing, but just get some feeling about how to create ER diagram like in practice, right, instead of drawing down on a piece of paper. Right? So let's think about Digitech, right? So let's try to think about how to model one application that looks like this. If you think about this application, right, what information do we need to store, right? I mean, of course, I have a whole bunch of product, right? So, and for each product, I have attributes, right? So I have a price, right? So, and also there's maybe there's some information that makes sense to be modeled as an entity instead of an attribute. For example, if you take this notebook as example, right? So you have the processors using, right? So maybe we should also model that. So let's try to think about this. So what type of entities do we have in this example? So I have the product, right? So what I can do is just click this entity, right? So you can actually introduce one entity here. So let's say there's a product, right? And then yeah, so maybe let's model maybe at a lower level, like notebook. And then what attribute do we want to have? Right. So attribute has the attribute ID, right? So what is attribute ID? If you just click this, so you'll probably see essentially this thing is probably essentially the product ID, right? So that uniquely identify a product, right? So that's an attribute. You can actually connect this attribute, right, with this. And you can say, so there are different properties, right? So, and then I can actually, yeah, here is actually means it's unique, right? Because a key. And you can see whenever you click this, you have the underline here. And the notebook has price. Let's have another attribute, the price of the notebook. Right. Yeah. And as you can see, right, so in the full specification of ER diagram, you can actually specify actually more things than we talk about. For example, you can make some of the attribute optional, right? Meaning that maybe the notebook doesn't have price, right? You can make them multi-valued, right? Something like this. Okay, so and then we have maybe another entity. Let's try to think about the processor, right? So each notebook has a processor, right? So you could model that as an attribute to say, this notebook has this type of processor, right? But here, if you think about this, essentially each processor has its own essentially attributes, right? And in this case, it actually makes sense, make more sense to model processor as a different entity, right? So because the processor can also participate in actually multiple relationships, right? So for example, here you could have another entity, processor, right? And then what attribute do we have? We have, for example, the name of the processor, right? Let's also give it like an ID to identify it. And you have just, for example, you have the release year, something like this. And you can actually connect them. And for this ID, right, so you can say, this is a key. Okay. So now I have two entities. And then we can actually build relationships between them. Have one relationship. For example, like notebook has a processor, right? And you can connect them. And then for this one, you can actually have some cardinality constraints, right? So here is actually, they're actually labeling the participation, right? So for example, one notebook only has essentially one processor, right? So essentially there's actually a many to one relationship from notebook to processor, right? So if I write essentially the like one n notation, I will have n here, I have one here, right? So I think here in this tool, they're actually doing participation, right? So it's very similar to the min-max like notation, right? So you have this. You can say this is a different flavor, right? So like there's a n, there's one here, there's like if you know notebook, you know the processor, right? You can do this. Or you can do the exact kind of cardinality here, right? So like the notebook always have a processor. This was very weird. Yeah, anyway, yeah. So like sometimes you can have those like exact constraints with the min-max notation, right? Here you can do this one notation, right? So this just like in practice, just one very quick example for you to see that in practice there are tools kind of to help you. Okay, so and also in tools like this, whenever you have a ER diagram, right? So there's also some semi-automatic tool to help you to translate this into a relational schema. Okay, but we are going to talk about the principle first, and then we see how this tool do it. And also this tool will not be in the exam, right? It just to show you that in practice, people do not draw this on a piece of paper, or people do not draw it in PowerPoint, right? People have tools to help you to do it, right? Whenever you are doing this in practice, we are doing real applications, try to find the tool, okay? Just don't write ER diagram on paper, okay? Okay, so now let's move on. So we talk about the conceptual modeling, right? To really to specify all the concepts you have in your applications. Now we need to implement that in some way, right? And that comes to the second part, that is logical modeling. So what is logical modeling, right? So on one side, you have your entity relationship model, which is the conceptual model. And we want to translate that into some data model, right? If you are using a relational database, then you are trying to translate this into a relational model. If you are using some other type of database, like for example, a graph database, where the data model is a graph, then you are trying to translate that into a graph, right? So in this course, we focus on relational model. So the process of logical modeling is always from a conceptual model, which is ER diagram, to a relational model. And concretely, we want to take as input this ER diagram that we have and output it into a relational schema, which contains a whole bunch of relations, each relation and a whole bunch of attributes, right? You can think about them as table. Okay, so this process is logical modeling. Okay, so just refresh our memory, right? So we talked about relational model last week, right? So a relational database has a whole bunch of relations. Each relation look like a table, right? And once you have that, you can actually query it. You can do relational algebra, you can do relational calculus, right? In practice, you can write SQL queries. And we went through the really beautiful like connection between different subset of SQL queries and relational algebra, relational calculus. Okay. Whenever you are doing this type of translations, what is the principle? So the principle is for all the entities in ER model, they become relations in the relational model. Pretty much every single entity side will become like a table, right? So relationships in ER model will also become relations in relational model. And whenever you have relations with the same key, right, in the relational model, you can try to merge them, okay? And there's different ways to deal with generalization, and we are going to go through them. There are different ways to deal with weak entity. We are going to go through them. Okay, so this is just a high-level principle. When you apply this principle, is going to get more complex. We are going to go through them. So I think there's some questions, right? Other questions? If you have a question, just speak up. So I don't have, so I cannot go through all the messages in real time. Okay. Okay, cool. So let's try to apply these principles. So first thing is for the entity side in your ER model, they become tables or relations. Okay. So and the attribute of the entity side in the ER model become attributes of the table or relation. So for example, if I have a ER diagram look like this, I have one entity side which is employee. I have 3 attributes, right? So I have SSN, which is the you can think about it as ID, the social security number in the US, right? So you have SSN, right? You have name, and you have age, and SSN is the key. In this example, right? So when you do the translation, this one becomes a relation that looks like this. You have the employees relation, right? In the relational model, has 3 attributes: SSN as a key, name, and age. And essentially, you can say like every single attribute become one attribute here, right? And the name of the entity side become the name of the relation. Okay, so far so good, right? So this kind of very natural. Right? So if you have any questions, just speak up, right? So if you type in the chat window, I cannot just follow all of them in real time. Yeah. Okay. Cool. So now let's talk about relationships. When there's no cardinality constraints, the thing is kind of very simple. A relationship in the ER model become a table, right? Contain the keys of all the participating like entities. Right. So for example, right? So here I have a ER diagram with 3 entity sites. I have department, I have locations, I have employees. And for department, I have a key, which is department ID here. For locations, my key is address. For employees, my key is SSN, right? And then I have one relationship among them, which is works in, okay? Which means that this employee works in this department at this location. And this works in relationship also have one attribute called since, right? So when you want to translate this relationship into relational model, right? Here I do not have any cardinality constraints, right? So one way to do it is it will become a table that looks like this, right? So the name of the relation works in is consistent with the works in here in the ER diagram, right? And then it contains the key of employee, which is SSN, contains the key of location, contains the key of department, right? It contains all the keys in the participating entity sites. And then it also have an additional attribute, which is the attribute of this relationship since, right? You have here. Essentially, this relationship in the ER diagram is going to become this actually like this relation in the relational model. So one thing we need to be careful about is it's very easy to see that you should have 4 attributes here, right? Because it's natural, right? So like to participate in this, you have 3 entity sites and you have 1 attribute. It becomes like a relation with 4 attributes. So what is the key here, right? So the key here, because I do not have any cardinality constraint, right? So the key is the combination of SSN, the address, the department ID, right? Which is a combination of the keys of all the participating entity sites, right? So why is this a key, right? First one is a set semantic, right? So I cannot have like duplicate here, right? So, and also because I do not have cardinality constraints, I'm actually allowing essentially all the possible subsets between SSN, like all the cross product between SSN, address, and department ID, right? Because I don't have constraint, right? So, and here essentially the best thing you can do is the combination of these 3 attributes, right? Become the key. So whenever you have kind of one relationship connecting entity sites of the same type, for example, you have employee report to another like employee, right? So there's a one relationship reports to. You have the role here. You have one is supervisor, another is subordinate, right? So in this case, when you do the translation, the name of the role can be used to distinguish between essentially these two different attributes, right? So here we'll do a translation, right? If you do not have the role, right, both of them will have SSN, which is not allowed, right? So you don't know which one is which, right? But you have essentially the role here, right? One employee is a supervisor, and another employee is a subordinate. So you can actually write the name of the role, right, to distinguish different attributes. Right? That's also very natural. So Kinetic is tricky. Okay, so then let's go through a little bit about more example here. So let's take this example. Right. So it's the same as the example that we saw before. You have department, locations, and employees. And I have the working relationship connecting these three different entity sites. The difference is now I have a cardinality constraint. Here I say, okay, if I know the employee, if I know the location, the combination, I can uniquely identify the department. Okay, so this is what I'm trying to say in the ER diagram. So when you do the translation, right? So if you still do this, that is, you have four attributes and you have SSN, department ID, and address as the key. This will cause a problem, right? So if you think about why, like is that in this ER diagram, right? So given the address, given the SSN, you can already uniquely identify the department, right? So this is the cardinal constraint I have here. If you have the combination of this here, right? So this is actually not the key because that's not the minimal site to uniquely identify a tuple in this relation. Does that make sense? Because of the cardinality constraint, right? The combination of these three is not a minimal set anymore, right? So in this case, we're going to do the translation, right? So instead of having these three attributes as the key, you should have the address and SSN as the key. Okay, that makes sense? Because from this, I know if I know the location, I know the employee, I can uniquely identify the department, right? So essentially to identify one participation in this relationship, I only need the key of two entity sites instead of the key of all three entity sites. Okay, that makes sense. Yeah, again, so it can be even trickier. So let's look at this example. So it's a little bit simplified, right? So I have the working relationship between employee and department. There's a many-to-one relationship. Means that if I know the employee, I know the department, right? So there's, yeah. And when you model this, right? So the working relationship will become the working relation here, right? If you think about what's the key, because the cardinality, right? So the key of this working relation will be the key of the employee, the SSN in this scenario, instead of the combination of SSN and department ID, because if I know SSN, I can already decide department ID. So the combination of SSN and department ID is not the minimal set of attributes to identify a tuple, right? And then whenever I do the translation for employee for this entity site, I will also have something like this. I have the key as SSN and I have the name of the employee. So when I do the translation, right, of this relationship and this entity site, I have these two relations. So if you think about this, both relations have the key SSN, right? It could be merged into a larger table, right? So in this case, another way to do the translation is I have another relation employees has SSN, has name, and I also merge this works in relation into this large table. I just put department ID here, and I put the attribute since. So these are just two different ways that you can translate this ER diagram into a relational model. You could have two tables, or you could have one table. So now let's think about which one is better, right? And also what's the pros and cons for each one of these. So if you compare the first one with the second one, right? So one thing that is good about the second one is that it's actually involve fewer amount of relation, right? So essentially, for example, whenever I try to get the department that the employee works in, right? If you model in the first way, I always need to do a join between these two relations, right? But if you model it in the second way, whenever I pick, whenever I get information of one employee, I automatically already get the information of department that employee works in, right? So some query will actually be more efficient if you model data in this way, in the second way, simply because it involves fewer amount of relations. But on the other hand, the first one is also could be beneficial in the sense that, so there's one interesting consequence of modeling it in the second way. That is, you are actually assuming every single employee must be associated with a department, right? If you have employee who doesn't have a department, you are going to put the null value here, right? Because then I don't know what department that employee works in, right? So if you model in the second way, and if you have a lot of employees who do not have a department, you are going to have a lot of null value here, and potentially you are going to have a larger relation here because you have a lot of empty kind of slots. You can think about that like that, like in your relation. But if you model in the first way, right? So like you will actually have a working relation that's actually much smaller, contains fewer amount of tuples compared with employee relations, assuming there are a lot of employees who do not have a department. Okay. So that's the pros and cons, right? So which one is better? It actually depends on your application. Okay. So now let's look at another example. Still the same ER diagram. Okay, I have employee, works in, I have department. So and when I do the translation, right? When I do the works in, I have this. When I do the translation of department, right? So I have a relation like this. I have department ID and the budget. I mean, this is very natural. Can we merge them? Right. So like previously in the last slides, right, we talked about if you merge the works in relation and the employee, well, there are pros and cons, right? According to your application, maybe you want to choose one or the other. But here, can we merge works in a department? Right. So in this case, what would you get? You get something like this, right? So I have SSN, I have department ID, and since, right? So all these three attributes come from the works in relation. And then for each department, I just put the budget here. Okay, I can merge these two. So what are the pros and cons for these two options? So this is actually a kind of a different scenario in the sense that in most of the cases, most of the cases, you actually do not want to merge them. So if you think about why, the fundamental reason is they do not share the same key, right? So the key of the working relation is SSN from the employee side, and the key of department is it's a department ID, right? So and the department ID is not the key here. When you merge them, right? So you are going to have a lot of redundant information. For example, I can have two employees work in the same department. They will correspond to two tuples in this relation. And because it's the same department, right? So they will associate with same budget. In this case, I'm actually storing the information in the department table multiple times if I have multiple employees working in the same department. Okay. Essentially, whenever you merge them, the second option will actually explode really fast, right? So in the majority of the cases, you do not want to merge them because they actually do not share the key. let's also look at cardinality. Okay, so look at this. So you have 3 entity sets, A, B, and C, and I have one relationship R connecting them. And from the cardinality, you can see essentially the information you want to model is I have, if I know A and C, right, I know the value of B. If I know A and B, I know the value of C, right? So this ER diagram tell you these 2 constraints. When you do the translation, right, the relationship R will be translated into a relation with 3 attributes, A, B, and C. I think that's very natural, right? So the question is, what is the key of R, right? So let's go through essentially all the 8 combinations and try to reason about it. So can we have relation look like this? Can we have A as the key of R after the translation? So like in this case, like no, right? Because I could have a database instance according to this model with multiple in which the same attribute A participate in multiple relationships, right? So if you model it in this way, right, I mean, it's not really a process model because here you are only allow the same value of A appear once in this relation. Okay, so this is not really a good translation. So similarly, right? So this is the same, right? So you like can I have B as the key, right? I'm the same, right? So from this ER diagram, right, you potentially you could allow a database instance in which the same value of B participate in multiple relationships. So B itself is not a good thing to have. Similarly for C, right? So because it's symmetric, right? So how about this, right? Can I have a relation R? And my key is the combination of A and B, right? So in this case, actually fine, right? Because from this relation, from this ER diagram, right? So from this cardinality constraint, you can see if I know the value of A and B, I know the value of C, which means that the like one unique combination of A and B can only appear once, right? In this relation, right? And therefore, if you set A and B as a key, it's actually okay, right? So you are not eliminating like too many like essentially you are modeling pretty much the same thing, right? And then can I have B and C as a key, right? So in this case, no, right? Because if you look at the ER diagram, right, it is possible that the same value of B and C appear multiple times, right? Because here's the N, because like for each of the combination of B and C, right, it might be associated with multiple value of A, right? And that case is not really allowed, like you are setting B and C as a key. Can we do this? Yeah, so you can still do this, right? So you can set A and C as a key, right? So from the ER diagram, you can see, if I know value of A and C, I know the value of B, right? So I could have A and C essentially as a key. So if you look at this case, if you look at these 2 cases, right, you can either set A and B as a key or A and C as a key, right? So you are allowing whatever database instance you are allowing your ER diagram, you are actually also allowing here, which is fine. The caveat is that if you set A and C as a key, you are still actually missing some information, right? So essentially, you are actually missing one of the constraints that A and B can also be a candidate key, right? So after a couple of weeks, we are going to talk about how to introduce essentially multiple of those constraints, right, in a practical database systems. Okay, so here we are talking about essentially A and B is a candidate key, A and C is a candidate key. Okay, whenever you are picking one as the primary key, right, and if you do not specify the candidate key, right, so you are going to lose that information, right? But again, this is a valid kind of translation, right? And whether I can have A, B, and C, right, the combination of 3 attributes as a key, right? So in this case, no, right? Because if you look at the ER diagram, right? So, because of the kinetic constraint, right? So the combination of A, B, and C is not a minimal set, right? when I know the value of A and B, I know the value of C, right? So it doesn't really make sense to have all three attributes as a key. Can you have this? Can you have a relation where there's no key, right? That's not possible, right? Because every single relation need to have a primary key. Okay, so this is just one example here. Essentially, for like given a kinetic constraint, right? You can actually get a whole bunch of candidate keys out of it, and you can pick one as a primary key. Okay? So in this example, the candidate key can be AB and can be AC, right? You can pick one as a primary key. Okay. Cool. So how can we deal with weak entities? Yeah, go ahead. There's one question. Go ahead.
Sorry, maybe that I'm asking this question again, but okay, so it's just that I can maybe finally finish this off, because B and C have this one constraint, and the A has the many constraints.
Yeah.
If I have, that means C, an instance of B and of C could still appear multiple times in the table, but it mustn't be that the B and C are combined multiple times, right? So if I have, let's say I have A1 and A1, B1 and C1 as a relation in there, and A1, B2, C1 in the relation, is that allowed? Okay, no. A1, B, C2, okay, forget it. I'm just kind of confused.
Yeah. So yeah, go ahead, right? So like here, essentially it means that a unique combination of A and C can only appear once, and combination of A, B can appear once.
But
because you are looking at the one here.
B and C can appear multiple times.
Combination of B and C can appear multiple times. Yes.
Okay.
Yeah.
Okay.
So for example, you could have A1, B1, C1. You could have A2, B1, C1. That is. This is fun. You could have this.
Okay.
Right. So you have a little bit like this, which means essentially, if I take a unique combination of A and B, I decide C, right, which is fun, right? So so like like A1, B1 only appear once in the whole thing. A2, B1 appear once is fun. And A1, C1 appear once. A2, C1 appear once. And in this case, B1.
And would A3, B2, C1 be still allowed?
Yeah, can you say it again? Yeah, sorry, A3,
B2, C1.
You mean the database with all three tuples?
Yeah.
Let's check, right? So I don't know, right? So it's always, but I know how to get there, right? So you check all the combination of AC, A1, C1, it's okay. A2, C1, AC is fine. You check AB. Yeah, this is allowed, right?
Okay.
This is fine.
Thanks very much.
Yeah. That makes sense?
Makes sense.
Cool. Okay, great. So weak entities, okay? So let's look at this example. So I have weak entity, which is room, depends on building. Building has the kind of strong key, right? The building ID, and there's a weak key, room ID. So here, you actually do not really need to translate this. We're gonna do a translation. So essentially, if you have the like one relation for building, one relation for room, right? So the key of the room relation will always be the combination of the strong key and the weak key, right? So it'll always be the room ID and building ID as a key of the room. This already have all the information that you want in the locating relation. So essentially, you do not, when you translate the whole thing, you do not need to have a locating relation in your relational model, right? Because you already have all the information in the room relation. Okay, generalization. So let's look at this example. So you have three entity sets. I have assistant and professor. Both of them are employee. Okay, this is the parent. This is the child. And then for employee, I have name. I have a personnel number. For assistant, I have the area. For professor, I have the level. Okay. So how can we do the translation here? There are actually multiple ways for you to do that. So one way to do it is to have these three tables as our three relation. You have employee, you have professor, you have assistant. And then you put essentially the shared attributes in the employee table. You have personnel number, you have name. Okay, for every single employee, may it be an assistant, may it be a professor, we don't care. You put them all together into employee relation and you put their name. Okay, and you have one relation professor which contains a subset of employee, and you only store the level. This is the attribute that unique to a professor in this example. And you have another relation which is assistant. Again, you store a subset of employee, and then you put their area, which is the attribute that unique to assistant. Right. So this is one way for you to model this. So another way to model this is to have a relation that look like this. You have essentially a professor table contains essentially all the attributes, both those that unique to a professor, like level, and also that you kind of inherent from the employee. You put name also here. For assistant, it's the same. You have personnel number, you have area, right? You have name. And then there could be employees who are neither an assistant nor a professor, right? So you could have an employee like entity, right, who is actually not assistant nor professor, and you put those in the employee table. Okay, so you can also do that. So there's actually two different ways for you to deal with generalization. So which one is good depends on your essentially on your application. Okay, so and also depends on what type of query that you are going to ask. So it's very hard for us to give kind of a general criteria about which one is good, which one is bad. But whenever you are building something real, just remember there are at least two ways for you to model generalization. Okay. Cool. Yeah, go ahead. There's one question.
About the previous slide.
Yeah.
Since the professor and the assistant already contain the name, aren't we able to just completely delete the employee relation?
No. So from the ER diagram, right? So you still have three entity set. There could be some employee who is there could be some employee who are not assistant and also who are not professor, right?
Ah, okay, I got it.
Makes sense, right? Yeah. Go ahead. There's another question. Go ahead.
But we do introduce some redundancy here by storing the name twice in professor and employee, for example.
No, if you store kind of disjoint set here, right? So like for example, for one entity, like right, so that entity is either a professor or an assistant or neither of those. Okay, right? You store all professor here, store all assistant here, and you store all other employee here, right? So there's still no redundancy. Right?
All right, thanks.
Yeah, go ahead. Another question.
Who? Oh, okay. Then another question, maybe regarding generalization. How would we model it if we know that that an employee is always either professor and assistant? How would we model that? If it
okay, okay, so there are actually two essentially two aspects of your question. First one, in the ER diagram, how can we specify that? Right, and second, in the relational model, like what can we do? So in the ER diagram, I believe there should be a way, but I don't know. Yeah, so there should be a way in the ER diagram to do that by having some other notations. But I don't know how to do that in the ER diagram. I can look it up. In the relational model, right? So if you know there are no other employee here, you don't need to have this relation, right? You can only have the professor relation, have the assistant relation, and you are done, right?
Thank you.
So but the problem is that if I give you this ER diagram, you cannot remove this employee table, because from this ER diagram, you are allowing to have employee who are neither assistant nor professor. Make sense?
Yes.
Perfect. Okay. Any other questions? Yeah, go ahead. I think there are another question. Michael, yeah.
Yeah, so here we have the person number that should be unique across all three relations, right? How do we specify that?
That's a very good question. So, so here, ideally, right? So we want these three sets to be disjoint, right? We do not want the same personnel number appear multiple times.
Yes.
From this relational model, you cannot specify that. So next week, when we talk about integrity constraint, you are able to do it in a real database system. Yeah. So here, essentially, you are actually missing that constraint, right? So essentially, there will be constraint that get lost during the translation process, and that is one example, right? So when you do this translation, you are going to lose that information. Okay, so if that's really important to you, by the way, if that's really important to you, you do this. You do the first option. You don't have that problem, right? So here you put the name of all employee here is unique by nature, right? And then I have a professor here, and then I have a distant here, right? So then you don't need to worry about redundant information. And this one has additional problem. You need to make sure all the personnel number in professor table must be one of this in the employee table, right? So you can do that. Next, you can see how that using something called foreign key, right? But if the uniqueness of the personnel number is really important to you, you can always do this. That makes sense? But when you do the translation, there will be constraints that get lost. Yeah. So and later on next week, we are going to learn how to bring them back if they are really important to you, right? But from the relational model, there will be constraints that get lost. Yeah. Cool. Any other questions? No? Okay, great. Cool. So that's all for today. When you go back home, right, try to look at this example, right? So this ER diagram, this is one of the kind of not the best translation maybe, but one reasonable translation. Okay. So and you can actually look at it, and it should be very clear about why we have something like this. Okay, cool. So that's all for today. Yeah, so I'll see you guys on Wednesday. Otherwise, I'll be here to answer whatever question you have. Okay, thank you.
Is that an actual table, like the relational model of UniDB? Is that, did you actually, does that actually exist?
You mean this?
Yeah.
Exist where?
I don't know. If you just made that, like if you just got that from somewhere, or if you just made that up for the sake of like showing us, or like showing us an example.
Yeah, we just make. Yeah, so we just make it up. Yeah.
Ah, okay. I was like, it saw some names. I was just like, huh. Okay. Anyway, have a nice day.
Yeah. You too. Okay, so if there's no questions, I'll see you guys on Wednesday. Yeah, have fun.